Hello, and welcome to the Nokia Technology Vision webinar on the road to quantum technologies, breaking classical boundaries. I'm Stefan Kind, Senior Principal at Nokia Strategy and Technology Organization and the lead editor for our Technology Vision. I'm very pleased that you can join us today and hope you will enjoy the session. This is the final session of our 5-episode Technology Vision webinar series. So today we take a closer look into quantum technologies, evaluating quantum computing, but also the potential of quantum communications, quantum security, and quantum sensing. I'm delighted to be joined for this webinar by my colleague, Michael Eggerson. Michael works as a research group leader at Nokia Bell Labs, and he's also the content lead for quantum technologies in our Technology Vision team. So after today's presentation, which will last about 45 minutes, we will have time for Q&A. So please use the Q&A function, which you find on your screen on the bottom, and post your question there. And we will try to do our best to address all of the questions at the end of the session. For further information, please also check out further details on the Technology Vision on the dedicated webpage, nokia.com/innovation/technologyvision, or on the specific pages towards quantum technologies. You will find the links to the resources with the icons on the bottom of your screen under resources, and just click there and you'll find the direct link. And now, without further ado, let me hand over to Michael. The floor is yours.
All right, thanks, Stefan. All right, I'm excited today to talk about quantum technologies. So before I dive in, I always like to start with a definition. So what do I mean by quantum technology? And really, quantum technology started in the 1930s and 40s, and it was really spurred on by the invention of quantum mechanics, which was basically the discovery that at a fundamental level, everything in the universe are discrete particles, and you have discrete energy levels. And so scientists and engineers started harnessing this to build really new classes of devices that we'd never seen before, things like the transistor, lasers, solar panels, even MRI. Right? And these are all technologies that are now ubiquitous today. And they all really fundamentally rely on ensemble behaviors of discrete quantum particles, and really are only possible because of quantum mechanics. And we call these technologies quantum 1.0. Now, today we're really at the beginning of a new era of quantum technology, which we like to refer to as quantum technology 2.0. And really, our methodologies and our understanding has improved to the level we're now able to actually harness, detect, and manipulate individual quantum systems, so individual electrons, individual photons, and also harness some of the unique properties of quantum mechanics like superposition and entanglement to create, again, a completely new class of technologies. And that's what I'll be talking about today, things like quantum computing, quantum communication, and quantum sensing. All right, so before I go into the technical part of this, I want to start with just kind of a high-level motivation of what's really driving a lot of this innovation. And there's a huge amount of potential impact in the quantum space between these kind of three different quantum domains. And there's a lot of investments to make these technologies happen. So these are some numbers mostly from McKinsey showing that the quantum technology market by 2040 could have a potential direct market of up to maybe 170 billion. With potential downstream value from the people and the companies using quantum technologies in the trillions. It's a really hot space. There's literally hundreds of startups, thousands of patents that are increasing every year, and a very large amount of investment. So about 42 billion just in public investment. This doesn't include investments from private firms. So it's a very exciting space. It's a very fast-moving space. So you probably see a lot of headlines in quantum, really on a day-to-day basis. And these really fall into one of these four buckets, which I'll be talking today. So we have quantum computing, and that's where I'll start, really harnessing these individual particles to do new types of computation. Quantum security, which is largely about protecting our networks and our communication infrastructure against the threats of quantum computing. Quantum networking, which allows us to communicate in new ways. And quantum sensing, which allows us to really go deeper into how we actually sense, understand, and track the physical world. All right, so what are the underlying physical principles? And this will really be my only really physicsy slide here. So when you're at a single particle level, you can actually create what's called a qubit, and this you can think of as the information container in these quantum systems, much like the bit is for classical communications. And so I have a kind of a diagram of here on the left. You can think of a classical bit as 0 or 1, it's on or off. And with a qubit, what makes it unique is it's no longer on or off, it's actually a vector, right? So we can think of this as a vector pointing somewhere on a sphere. And so you can kind of get an intuitive sense on how there's a lot more informational space in this information container, because instead of just on or off, you can actually point in any direction on this sphere. Now, there's two principles that kind of enhance this information capability. One is superposition, and that's really the idea that these qubits can exist in multiple states, which I'm referring to as a vector, right? So they're not just up or down, but they can be in any direction. And superposition isn't just for one qubit, but you can actually combine multiple qubits, something we called entanglement, and put large numbers of qubits into a joint superposition. And so what this means, when you entangle two qubits, you're basically making it so if you measure one qubit, you know something about the other. And it's this kind of fairly simple property of being able to combine two qubits in a way that you know one if you measure the other actually gives you a lot more abilities to do things like computation and communication. And so these are really the underpinning kind of physics concepts around quantum 2.0 technologies. All right, so let's start with quantum computing. So quantum computing is a very big field. About 75% of the investment today is going into quantum computing, whether it's at the very bottom physical layer where you're actually making new types of qubits, and there's literally dozens of types of qubits, all the way up to the application layer on how we actually use quantum computers, how we write algorithms, how we access them, and actually how we write programs that utilize the power of quantum computing. All right, so the promise here really is the ability to solve intractable problems, right? So there's a large set of problems that you can't compute on a classical computer, and you really never will, no matter how much computational power you have. These are things like large-scale optimization, like network optimization, problems in cryptography, drug simulation, specifically like quantum chemistry and simulation, things for developing better materials, drug discovery. And also new avenues in AI/ML. Right? So quantum computing you can think of as a completely new way of computing. And so there's a lot of promise here to create new types of AI that we've never seen before. And so when you look across all of these markets, there's a lot of market potential and a lot of really, I'd say, large human needs challenges, right? That have a huge kind of human benefit if we can actually solve them. We can actually make better drugs faster for lower costs, and we can reduce energy loss and waste in our global logistics infrastructure. All right, so to get to this point where we can actually solve these problems with quantum computers, what do we need? Well, really, we like to think of these three fundamental ingredients that any useful quantum computer would have. First of all, you need stable qubits. So if you have a qubit and you set it as a 1 and you walk away and you come back 10 minutes later, it should still be a 1. Second of all, you need high entanglement. You need all of your qubits talking to each other and you want them all entangled into one large superposition. If you can't entangle them all together, if they can't all talk, that really limits the capabilities of a quantum computer. And finally, you need high scalability because hundreds and thousands of qubits isn't going to be enough. Even for the first kind of simplest useful quantum problems, you need hundreds of thousands of qubits, if not millions. And that's just to get started on the road towards useful quantum computing. Now, unfortunately, when we look at the reality of quantum computers today, we see problems in all three of these key areas. First of all, you have qubits that are incredibly noisy. Most qubits today lose their information in less than a second, typically less than a millisecond. You put in a 1 and you come back a second later and it's just random noise. And so this makes it very, very difficult to actually scale up the problem you're trying to solve because all of your information disappears very quickly. Second of all, most quantum computers, they have very limited entanglement. You're entangling nearest neighbors, and because of lifetime issues, because of basically physical limitations of how you make connections, it's very hard to actually get large groups of qubits entangled together. And finally, these systems are very, very challenging to scale. They require extreme environmental conditions. They need to be pretty much near absolute zero temperature, which means you either need large dilution refrigerators or complex laser cooling systems. And this makes it very, very challenging to actually scale them up to large sizes and large computational powers. And so I kind of put together a roadmap here, going to there's a lot of companies working on qubits. This is just five of the companies out there, and this kind of shows the roadmap that most companies are on. And so on the horizontal axis here, we have a number of logical qubits. When I say logical qubits, I mean these are qubits that have error correction that allows them to be more error resistant. And so most companies out there, pretty much all companies, are envisioning that you'll use groups of qubits, you'll run an error correction code, and that will allow you to create a logical qubit. And this is the same as we do in the communication industry, right? We're not just sending bare bits, we're sending them with error correction. And then second of all, you have your logical error rate. Right? So if you do a computation between two qubits, what is your chance of error? And you can see that right now, we're down here where a lot of companies are starting to show roughly one logical qubit and error rates about 10 to the minus 4. But to get to where you'd actually be solving useful problems, you need to be up here in the top right corner. So error rates of below 10 to the minus 8 and at least 100 logical qubits. Actually, anything less than about 60 qubits, you can actually perfectly simulate on a classical computer. And so you wouldn't need a quantum computer at all. And so these timelines are all slightly different, somewhat similar, but we can see that most companies are predicting that maybe by the early to mid 2030s, you start to have quantum computers that have the computational capabilities to solve useful problems. Now, what these look like are very, very large systems, right? So this is just kind of some representations of what companies like IBM and PsiQuantum, two leaders in the field, expect these quantum computers to look like, right? So these are very, very large systems that basically take up an entire warehouse or data center. And it's not just quantum computers. So if you look at this figure on the left, each one of these silver boxes is basically one dilution refrigerator that holds a quantum chip at very low temperatures. Each one of these black boxes is a classical compute rack, which is actually required to operate the computer and to run error correction. And so you're seeing basically these will be very, very large systems that require a lot of power, a lot of maintenance, and a lot of engineering to get to this scale. And this is very similar across most quantum computing architectures. And so with this kind of vision of where quantum computers are going, how you would access this is really cloud computing, right? And so we see quantum computers being another type of compute. We can call it a QPU for quantum processing unit. So this will sit in data centers in the cloud next to classical compute, GPUs, NPUs, and it'll be another tool in our toolbox to solve complicated problems. And we'll have it, and basically there will be SDKs that can allow access to developers to use these different computational abilities. So as a user coming in from an application layer, a lot of this will be opaque to you, right? You will have a problem you want to solve, and then there'll be tools to help map that problem onto the right type of compute. Because depending on the problem, a CPU might be a better solution, a GPU might be a better solution, or parts of your problem might run much faster if they're on a quantum computer. All right, so I'd like to kind of just pause here for a second to do a sanity check because there's a lot of hype in this field. And so I just want to list some of the key milestones because a lot has happened in quantum computing in the last couple years. So first of all, there are quantum computers out there. You can go on the cloud and you can get access to real quantum computers that are running on real hardware. And you can do universal quantum gates, right? So you can perform kind of universal quantum computation. However, the error rates are very, very high. This is a problem that's really at the forefront of the field, is reducing errors. And there has been demonstrations of real-time error correction to start bringing down these error rates. But the physical error in these qubits is still around, at best, 10 to the minus 4. Now, as these quantum computers scale up, linking them, right? If you're thinking about a quantum computer spread across the data center, you'll need quantum links to actually connect them. And so we're starting to see some low fidelity quantum links in literature and demonstrations. And then a term you'll hear a lot is quantum supremacy. And so quantum supremacy is really the concept of, does your quantum computer outperform a classical computer? And this has happened for a task where you're basically creating random quantum states. It's not really useful for anything, but it is a benchmark that you can argue there's been quantum supremacy. Now, in terms of milestones that have not been achieved, there's really no demonstration of a useful application where a quantum computer outperforms in time or in cost what a classical computer can do. And that's just because they're not at the scale yet where they can do that. Error correction is still in its infancy. There still hasn't been shown any real-time, basically logical qubit gating, where you have two error-corrected qubits and you actually perform computations on them. And really, most multi-qubit gate operations have errors around 10 to the minus 4 or worse. Right? So still many orders of magnitude away from what you need for useful quantum computation. Now, if we look in the near term, about 10 to 15 years, there's things to consider when you start to ask, what kind of problems do I think these quantum computers can solve? And this is shown nicely in this plot on the bottom right. Quantum computers, they're slow. Right, so their clock speed is typically less than 10 megahertz, which means they have very limited input-output. They also have a low number of bit count. And so at best, maybe you'll be getting a gigabit per second I/O, which means they're not going to be good for solving big data problem. There's kind of a huge kind of overhead to loading your data in the system. So where they'll succeed is very large computational problems that require a small amount of data. Right? So the classic example would be like cracking an RSA key, where you only need a 2,000-bit number, and it's a huge amount of computation. So that's something that's exponentially difficult on a classical computer, but a quantum computer in the near term, in the 15-year horizon, would be a good fit for that. And then applications that require a large amount of data throughput, you can think like, image recognition or these large language models. Those are things that would be very difficult for a quantum computer to excel at, just because they rely on a very large amount of data. All right, so I just want to touch briefly on some applications of quantum computing. So this one's one of my favorite. This is kind of one of the exciting ones. It's in sustainable fertilizer production. So about 50% of the world population relies on human-produced fertilizer, so synthetically produced nitrogen fertilizer. And the process used to do this was invented over 100 years ago. And it's quite energy intensive. It requires a massive amount of CO2 and a massive amount of energy. And basically, it requires you to operate at very large temperatures and very large pressures. Now, if we look in the biological world, we can actually see there's bacteria that live in the soil that can do this same thing, and they can do it at ambient temperatures. They can literally just do it at normal, room temperatures and atmospheric conditions. But we, as scientists, don't know really how they do it. We don't know that process, which means we can't replicate it, and so we're kind of stuck with these more archaic, energy-intensive processes. We've isolated this molecule called, we as in the scientific community have isolated this molecule called FeMoco, which we know is responsible for the process of kind of this natural generation of fertilizers. But it's such a complex molecule, we have no way to really simulate it and understand how it works. And this is something that a quantum computer could do. Right? Quantum chemistry, simulating structures like this is something a quantum computer would allow us to do and actually gain insights on how this works, and hopefully use it to actually replicate this process to improve our ability to create fertilizer at lower costs and lower CO2 usage. And even a couple percentage increases in efficiency here could save literally billions of dollars and megatons of CO2 usage every year. Now, another application, which will be important for the next part of my talk, is really more of a threat of quantum computers, but it's cracking a lot of the asymmetric encryption we have today, such as RSA. So there's an algorithm known as Shor's algorithm that allows you to basically factor prime numbers very quickly, which is at the core of how RSA keeps our data secure. And if we look at Shor's algorithm, kind of the flow diagram here on the bottom, it's a mixed classical quantum algorithm where there's these steps in blue that can be performed very, very quickly on a quantum computer. So if you have a quantum computer of reasonable size, which would be several thousand logical qubits at very, very low error rates, maybe 10 to the minus 10, 10 to the minus 12, you could crack RSA in about 8 hours. Whereas a classical computer, even if you load it into the biggest supercomputer in the world, doing this would take you billions or trillions of years. So a good example of a huge computational speed up with quantum computing. So if we look at the impacts on this to the telco industry, obviously this last one is a very big one. Security is going to be very, very important in the quantum era, and making sure our systems are protected against these potential attacks. There's now for market opportunities, because we see basically these very large quantum computing data centers starting to be envisioned, there's going to be opportunity for really a new class of optical interconnects, quantum interconnects to connect them. And then on the application side, actually using quantum computers would allow us to make more efficient and resilient networks in the future, and also prepare for kind of different network configurations to prepare for things like equipment failure or really dense deployments. And so here we see a potential for a lot of efficiency gains by actually utilizing quantum computers. All right, so I just want to wrap up this part on quantum computing, talking about a bit what we're doing at Nokia Bell Labs. So at Bell Labs, we're working on a different type of qubit. And so what we're trying to do is solve that fundamental problem of instability in a qubit. And we want to make a qubit that can actually store information and perform computations with incredibly high reliability. And so we're building what's called a topological qubit. We build it in gallium arsenide. It's an incredibly common type of semiconductor. It's used in a lot of the laser diodes used around the world. And we can create quantum states that actually exist over the entire surface of a gallium arsenide chip. And so what we've shown is we actually create quantum states that are stable for days, even up to a week for some devices. And this really compares to the millisecond lifetimes of traditional qubits. So when you pair this with our expectation of being able to operate these at high speeds, at really nanosecond gate operations, and having devices that are very small, so you can see a picture here on the right. These are kind of about 10 by 10 micron squared devices. Basically, we have a platform here where we think we can create very, very stable qubits in a highly scalable manner, where you're just using traditional semiconductor processing. You can create millions on a chip, and you can do it on really a traditional semiconductor material. So there's a lot of excitement here, and stay tuned on our research results. This is a very, very active area for us, looking at really changing the efficiency and changing the scalability curves of quantum computing. All right, so there's one other topic within quantum computing, which we group in here, which is called quantum-inspired computation. And so this is very similar to the type I was just talking about, but these systems you don't really think of as a full kind of gate-based quantum computer. Really, what they use is physics and really the physical kind of property that systems want to decrease their energy, and you use that property to solve problems. And the problems you can solve are similar to a lot of the things that quantum computers should be able to excel at, things like optimization and network management. And the nice thing about quantum-inspired computing is there's ways of building it where you don't actually need a full-scale quantum computer. So you can do this often in digital logic, and you can do it faster with lower energy than both a classical computer and a quantum computer. And so this whole area of quantum-inspired computers started several decades ago. There's a lot of companies working in this space, companies like D-Wave, Hitachi, Toshiba, all of well-known systems. And there's a lot of ways you can create them. You can create them V-Wave has a quantum annealer, which uses basically qubits, but uses them in a certain way to do basically these annealing processes. You can build them in optics. You can build them even out of CMOS circuits. And so there's a lot of different ways that companies are trying to go after this to create really scalable quantum-inspired computers to solve really mainly optimization problems. So these won't be as useful for things like quantum simulation, but for network optimization, these will be useful tools. And so in the next, kind of 5-year span, we're expecting to see hardware platforms that can handle thousands of variables. And some of these are large systems that will be in the cloud. Some are small that could actually be on premise. So some of these architectures you can even deploy in an FPGA. 10-year horizon, we see the development continuing to scale with tens of thousands of variables, continuing reducing the energy consumption. And on 10-year or 10-year kind of horizon, we're seeing these systems kind of grow to very large sizes, where you can be computing on millions of variables, and you'll have really like application-specific implementations of this to solve specific problems. So this is something we are working on at Bell Labs as well. And an example of the kind of problems we're looking at is in a multi-user MIMO. Right. So in multi-user MIMO, you have multiple users. You're receiving all of their data across an array of antennas, and you need to sort out whose data is whose. And you can basically frame this as a combinatorial optimization problem, and then you can map this onto a quantum-inspired computational platform. So in our case, we use what's called a oscillator icing machine. So this uses CMOS-based resonators. And what we've shown is you can get very, very low error rates, and you can actually solve this very quickly. So you can actually kind of piece apart which data goes to which users, theoretically on a nanoscale, nanosecond time scale. And so we see this as a potential opportunity to actually increase the energy efficiency and speed of this very critical task with really a new class of computation. All right. So with that, I want to move on to quantum security. So as I mentioned, this is going to be a very important topic in the quantum era. And really, it's driven by these large quantum computers, which will be able to crack things like RSA. And so if we look at when this will happen, that's always the first question we get. When will we actually have a cryptographically relevant quantum computer? There's really no consensus. So we can see on this chart, this is kind of a survey of experts in the field. When do you think a large enough quantum computer will come around? And it's anywhere between 5 and 30 years from now. But you can say the majority of experts would say within the next 15 years, this will be available. And so this is something we need to start preparing for. So if it's 10 to 15 years out, why is it important? Well, one large problem is the harvest now, decrypt later. Right? So any communications you're sending out now can be stored by bad actors and then later basically decrypted once these quantum computers come around. So if you're storing information or sending information that needs to stay secret for very long periods of time, this becomes an imminent problem. Also, the deployment of a new type of security across the network takes a long time. And so it's something that we're actually getting started today. We've actually well along the path here. So if we look at the different types of cryptography used in network systems, we can kind of break it into two main classes, symmetric cryptography and asymmetric cryptography. So the symmetric keys, things like AES, these are considered quantum safe. So these are not something we expect quantum computers to be a huge risk for. On the asymmetric cryptography side, things like RSA, that's where we need replacements, and we can do replacements with either physics-based methods, things like quantum key distribution, or with math-based, right? So using more complex algorithms that even quantum computers wouldn't be able to crack. And so when we look at this across the network, we don't really see like a one-size-fits-all, and it's really a security in depth approach, right? So it'll be a combination of these things, of physics-based approaches, of math-based approaches, and applying these across the different layers of the network stack to really create the most secure system you can. And again, this is something that we're already doing today and getting started to prepare for this quantum future. Now, this is something that's, it's not just Nokia doing this. This is being driven by standards bodies. So really NIST started the process of standardizing, especially along math-based protocols. And then the results of this are then being pushed into other standards bodies. So things like IETF. And then this is now being followed up with incorporation into standards like into 3GPP. And one thing to note here is the approach to how you build a quantum safe network actually varies depending on where you are. Right? So there's different approaches being kind of championed in the US or in Europe. There's different kind of regulations, there's different suggestions. And so having really this layered, this security in depth architecture will allow us to actually span to more than just one area. All right. Now, as for what Bell Labs is doing in this space, so we've been doing research in quantum key distribution for quite a long time. So this is where you actually harness the property of entanglement, and you entangle two photons, send them over a link, and you can do this to share keys in a way that is impervious to eavesdroppers. And so what we've been working on is ways to increase the speed of this, and to do using traditional telecom equipment. And so this is just kind of a summary of some of what we've been able to do. We leverage basically advanced digital signal processing to increase these secret key generation rates to very, very high levels. And so over short distances, like a 14-kilometer link, you can reach secure key rates of hundreds of megabits per second. And this kind of brings us to our next point, because one of the biggest disadvantages of QKD is its limited range. So you can do this very well at short distances, but really once you get up to about 100 kilometers, loss in fiber makes QKD just kind of untenable. And so that brings us to our next point on quantum networking. So quantum networking is really about harnessing the full power of a single photon. So photons are a quantum object, they're discrete particles, and they're what many people like to refer to as flying qubits. Because it is a qubit, you can encode quantum information on it, and then you can send it over long distance through a fiber, through the air. And it's really the only known qubit that we know of that can actually transmit quantum information like this. And so some of the key research areas in this field are reducing loss, right? Things to extend the range of things like QKD, and creating new devices that allow you to really expand not just the range, but really build networks that can send quantum information over very long distance. And then unlocking new limits. Quantum networking is much, much more than QKD. There's a lot of other applications, both in sending classical information, but also in how you synchronize quantum sensors, quantum computers on a global scale. And so the way I like to look at quantum networking and quantum communication is kind of this layered approach where, at the top we have our normal classical coherent detection. This is how all of our optical communication works today. You think of light as a wave. You use classical lasers and classical detectors. One step towards full quantum networks is quantum detection, where you're still using a classical laser that sends out many photons, but you're using a single photon detector, which is allowing you to detect really individual photons as they come. And what I'll show later is you can actually use this to do very, very energy efficient communications, far beyond anything a coherent system could do. Going one more step quantum, we have a quantum link. We're actually using entangled photons. And there's many different schemes. You can entangle multiple photons and send them together. You entangle two photons, keep one and send the other. That's what QKD does. And so these quantum links can do things like secure key exchange or applications like efficient communication and very noisy channels. And then finally, kind of the fully quantum communication part would be distributing entanglement. And so that's where you actually have entangled qubits. You have them coupled to a qubit on one side of a network, and you're basically distributing the entanglement over a large distance. So you can entangle qubits at very, very large distances. And so this will be important for things like distributed quantum computing, as well as quantum internet, which I'll talk about in a couple slides. All right, so before I do that, I just want to talk about what we're doing in Bell Labs on quantum detection. So this is work that's been going on for several years, and again, what we're using single photon detectors on the receiver side, but the rest of the link you can think of as classical. And I have a somewhat complex plot here on the left, but basically it's showing you what the bounds of a fully classical coherent system is, which is in red. And if you look at pretty much all of our communication systems, you see low efficiency. So you need a lot of photons to send information, but a large capacity. So what quantum detection allows us to do is actually send very, very large amounts of data with a very small amount of power. So our record right now is 14.5 bits per photon. And so this is incredibly useful in areas where you have very, very low energy. A good example would be in non-terrestrial communication networks, where you have to send information maybe from the moon to Earth or between satellites, and you have a lot of optical loss. And this allows us to actually have very, very large data capacity, even at low energy. All right, so this is, again, just one application of quantum communication. Now, to realize all types of quantum networking, quantum internet, there's a lot of devices that need to be developed on the physical layer. Things like sources of entangled photons, deterministic single photon sources, detectors, detectors that work. These typically work at low temperature, but you need to be able to detect single photons at very, very high efficiency very quickly. Memories. This is arguably one of the biggest gaps in our technology right now. In any sort of networking, buffering is crucial. And right now we don't have a good way of buffering quantum information. And so that's where the need for quantum memories is for scaling out networks. And switches. So typical switches you see in communications now have high loss, and high loss just kind of kills quantum communication. And so we need to build better lower loss switches. And these are all things that are active research areas for us at Bell Labs. Things like very low loss, both active and passive circuits to do very high speed switching with low photon loss, creating integrated quantum sources and quantum detectors for these future quantum networks. And also we're starting to expand into quantum memories and trying to understand, how do we actually build a scalable device that'll allow us to do buffering at nodes in a quantum internet. All right, so with that, I've said the word quantum internet a couple of times, so I want to talk about really what I mean by this. So if we look at these quantum links that we see today, they're all point to point. We take something like QKD and we just have 2 points that are exchanging keys. And what we'd like to do is extend this like all of our other networks that go over long distances to multi-users. And so to do that, we need to start putting in intermediate nodes. And you can't just use a repeater like you do in a classical network, because quantum information can't be amplified or cloned. There's this thing called a no cloning theorem. And so there's a technology called a quantum repeater. And what this is it doesn't actually amplify or repeat, but you can kind of think of it as a way to hop entanglement distribution through a chain. So eventually, we're looking at a 10-year horizon. As we create these quantum repeaters and build out these networks, that'll allow us to actually scale these networks from being point to point to actually multi-user over multi areas. Now, in the meantime, what you're seeing in deployments out there is where you use trusted nodes. And so basically what trusted nodes are is you have basically multiple point-to-point networks, and each node in your network is a trusted point where you're breaking the quantum nature of it, so you don't have security at that node. And so obviously that's not ideal for a fully secure network and for exchanging quantum information. For example, that doesn't work if you want to do distributed quantum communication, or excuse me, distributed quantum computation. And so that's where we see quantum internet coming in. And it's more than just quantum key distribution, although that will be one of the big functions of a quantum internet. But you can also think of distributed quantum computing, delegated quantum computing, using the network itself to solve, to run algorithms like quantum consensus algorithms, but also to do distributed sensing. Right. So the next part of this talk will actually talk about quantum sensors. And if you actually want to distribute them over long distances to increase their resolution and their sensitivity, again, you need a network that can actually transmit quantum information. And so we see quantum internet as a second layer to the internet. You still need your classical internet, and you're still going to be sending information classically. Even your quantum communication itself typically relies on that classical communication channel. But this quantum internet will be basically a parallel layer that gives you this added functionality of being able to send quantum information. All right. And just a brief touch on what we're doing in this space in Bell Labs. So we're actually actively looking at architectures for the quantum internet, simulating actually how these would work, how you would actually build them, how you'd operate them, and building out what a protocol stack would be, because you can't operate them the same way as a classical network would. And we're also looking into error correction, right? So error correction is a key thing in classical communications. It's going to be even more important in quantum communications. So how do you actually develop efficient error correction for these quantum networks? It's a very, very, I'd say, hot area of research right now. All right, so this brings me to my last topic area, which is on quantum sensing. And so quantum sensing is really about leveraging quantum objects to reach really the absolute best sensitivity you can in any type of physical sensor. And so, as I mentioned earlier, qubits lose their information very quickly. And they lose their information quickly because they couple to the environment. And so they're very susceptible to noise. But you can actually leverage that sensitivity to build very, very sensitive sensors. And you can build a quantum sensor for almost any type of physical parameter. And so you can do it for position, for magnetic field, for temperature, for gravity. Basically anything you'd want to sense, you can use qubits to actually build a very, very sensitive version of that qubit system. So in this large class of things and of applications in quantum sensing, for telecommunications specifically, there's several that we think are very important, specifically those around positioning, navigation, and timing, all of those which are very critical to telecom. And then in other fields, we see a lot of exciting applications for things like bioimaging, infrastructure monitoring, and also environmental monitoring. And these technologies, because of really their breadth, they're being developed by a lot of different companies and a lot of different kind of, I'd say, hardware architectures are being looked at across a large number of really the classic players in the sensing market, but also new companies that come more from the quantum computing background, but are using those same technologies for sensing. So that's companies like Inflection. So what are some examples of these quantum sensors? I'd say one of the most relevant for telecom is quantum clocks. So quantum clocks are very familiar to us. We've been using them for a very long time. That's really what powers GPS, is these quantum clocks embedded in all of the satellites. And that's actually absolutely vital for synchronization and timing and telecommunication networks. Our technology on this has advanced, and we can actually now create quantum clocks on a chip. All right, so there's companies out there that are miniaturizing these, and they're not only bringing down the size, but they're bringing down the cost. So quantum clock on a chip used to be hundreds of thousands. We see in the next decade, these prices should drop down into the hundreds of dollars per chip or less. And this would allow you to actually embed quantum clocks into your actual devices, which would both safeguard against things like GPS-denied regions, but also improve things like your navigation, which again is fundamentally reliant on precise timing. Another exciting area is in RF sensors. So you can actually use these qubits to sense RF fields, and you can do this over very broad spectrums with high tunability. So this is just an example from the company Inflection, where they're actually working on this ultra broadband radio receiver based on atoms. So it's arrays of atoms, and then get very, very good sensitivity, very, very good tunability over literally gigahertz of bandwidth. And so we see this potentially opening up a new way on how we actually physically construct radios in the future, allowing them to be more reconfigurable and more dynamic. Now within Bell Labs, we're starting our research in quantum sensing. We've been looking specifically at quantum magnetometers. So magnetometry is very important for many applications, from imaging to navigation. And so what we do is we're actually building these out of nitrogen vacancies in diamond. So you take a piece of diamond, typically synthetic. You can actually take one atom out of the lattice, and when you do that, that vacancy actually acts kind of like a bar magnet that likes to align to the magnetic field. It's incredibly sensitive. And so you can actually get very, very, very high resolution magnetic field sensing from it. So sensitive to the point that you can actually look at the gradients of just the Earth's magnetic field. And by measuring that gradient very, very precisely, you can actually locate where you are on the planet. And so this would be kind of a backup to GPS and GPS starved regions, and another way to improve our ability to know where we are on the planet. But beyond just navigation, things like brain imaging or another exciting application of this type of magnetometer. All right, so with that, that I think is my 45 minutes. So hopefully that leaves us with a good amount of time for questions.
Yeah, thank you, Michael. A very fascinating presentation. I see a couple of questions coming in here. So for the Q&A part, we will also have Aritar Banerjee joining us. Aritar is a research scientist also at Bell Labs. And I think there are a couple of questions on clarifying questions. Let me probably on the last one. For quantum sensing with multiple geographically distributed sensors, why would a quantum network be necessary or desirable? If the quantum sensor do their work, the signal processing could be also done in classical networking way. Correct? So there's more clarification question.
Yeah. So it depends on what you're sensing. So if you're sensing like a local magnetic field, then having distributed sensors isn't going to help. If you're doing something like, maybe you want to do very sensitive seismography, where you're actually looking at collective oscillations across the planet, and you want to be able to actually share the quantum information from these sensors to synchronize on that level. We also see that in things like astronomy, where you can actually, general rule in astronomy, you increase your aperture, you increase your resolution power. You can do quantum sensing in the same way, looking outwards, but then you start running into limits if you can't actually couple these together. And so that those are the types of distributed quantum sensing applications. Things where you're just sensing local fields and you're kind of collecting that data together. Yeah, absolutely. That can definitely rely on kind of classical signal processing and data aggregation.
Right, excellent. Then I think there is a question more towards the beginning of the presentation on the classical computing. As classical computing is evolving, will this impact the limits when quantum computing becomes relevant?
Yeah, no, that's a great question. Because quantum computers are being developed and advances are happening at a very, very fast pace. But the same is true about classical computers, right? The classical compute is not standing still. And so, yeah, absolutely. I think it's a moving target. But I think really the difference is what kind of problems can be solved. So quantum computers can solve problems at a large enough scale that classical computers could never solve, no matter how big or how advanced they are, right? And so those benchmarks don't really move, because if your classical computer can never solve it, then it doesn't matter how big your classical computer can solve. And so those are the problems that we're really interested in quantum computing.
So which means it's not a 10x question, it's 100, 1,000, or 10,000x question, right? So
yeah. Yeah, like RSA is a good example. Right now, if you use the biggest supercomputer in the world, it would take about 1 trillion years to crack RSA. So if you made that 1,000 times better, it'd still take 1 billion years. So that's not really useful.
Right. Excellent. Okay, next question. You indicate near-term 10 to 15 years evolution for quantum computing. Will AI help to accelerate the evolution in quantum computing or even other quantum technologies?
Yeah, yeah, absolutely. AI is already being used in quantum computing. And just like we see AI in every other type of compute, it's multiple layers of the stack. One of the things where I think it has a huge, huge benefit is in actually characterization and control and calibration. So qubits, they're very sensitive, so they basically get detuned. So you have to constantly be recalibrating them. And this becomes a very, very complex problem when you scale up. And so we're already seeing deployment of AI to help with that, to actually help with that physical stability and calibration of qubits. But even in like understanding the problems you can solve better with quantum computers, again, I think AI is helping accelerate that.
Right, okay. Next question. Does the concept of quantum repeater violate the principle of non-cloning of qubits?
No, it does not. Yeah, so quantum repeater, I think, is just a poorly chosen name because it's not actually repeating quantum information. It's creating a hopping point. And so basically the idea is you have a qubit here, here, and here. And so you couple these two, and then you have that link established. And then you link these two, and so those two are established. And then at that central node, you can actually swap it. So instead of this middle one being connected to the two, this one can basically drop out and then just connect the two on the outside. And so it's basically kind of this game of chaining along your connections and then swapping them at the endpoints. And so it doesn't actually go against the no cloning theorem.
Okay, excellent. Thank you. Next question. Is post-quantum cryptography strong enough to resist to a quantum computer? When do we know about that, whether the new algorithms are stable enough or resistant?
I'll probably take that. So these algorithms that are being standardized by NIST, they are supposed to hold against both cryptographically relevant quantum computers as well as classical computers. We do have some in the pipeline that were actually standardized recently, and one was on key exchange or key encapsulation mechanism. The other couple were on digital signature algorithm, both primarily using public key cryptography. And what it does is it's essentially the same math that we used to have. It's not quantum math that actually goes into the PQC algorithm. It's a different form of math. It's a different mathematical hardness that underlies within those algorithms. And so previously it was based on the hardness of discrete logarithm. Now it's actually based, like one of the selected algorithm was based on the hardness of lattice-based cryptography on ring learning with errors. And so these concepts essentially are classical in itself, and the math is thought to have been hard for a classical as well as a quantum computer to break. Now we have certain algorithms in place, but it's like with any cryptography, it has to age like fine wine. So we need some time to actually let it sort of stew in a bit, because I remember, I mean, it's probably in the early 2000s. It also took a lot of time when these algorithms that exist today, like elliptic curves, and they took some time from being standardized to actually being implemented to actually being believed that, yeah, they will protect us against classical computation in the early 2000s. And I would presume that we need a bit more faith in these algorithms, but I'm not absolutely not saying that we shouldn't have faith in this algorithm. These are obviously very, very highly rated cryptographers, but nothing ever is unbroken. That's I think one of the motto that cryptographers say. So it's always a matter of time. But these algorithms do boast a very strong protection against quantum computers as well as classical computers. Obviously, the quantum computers part testing we can't do right now because we don't have the necessary stable qubits to actually break the RSA or the elliptic curve algorithms. And actually, because of this, there are some companies, not some companies, but actually a lot of governments as well as companies are also advocating for, based on your use case, to use hybrid mechanisms, which is like classical plus quantum, like PQC algorithms together, such that it can actually provide a sort of dual protection layer in case the PQC algorithm breaks. But at the end of the day, eventual migration would be complete PQC once the cryptanalysis is, well, I mean, sufficient, as I would say, but it's never sufficient. But let's see. Yeah. Sorry, I sort of overwent. Please, yeah, continue.
Thanks, Avatar. Very good. Another question. Will quantum computer hardware rely on quantum oscillators only, or will there be a need for classic frequency generation or oscillators?
Oh, yeah, so it depends on the type of quantum computer. So there's at least a dozen different types of architectures. So if you look at one of the most popular ones, superconducting qubits, that's what like IBM and Google are using. Those actually fundamentally rely on a lot of RF signal generation. So they're using classical oscillators to actually control gate and readout their qubits. And so because of that, we're seeing advances in quantum computing that are also pushing the classical hardware as well. So yes, I guess it would be the answer.
Excellent. Thank you. Let me check. I think these were the questions which were coming in. So, Michael, Aritar, many thanks again for taking question and for the great presentation. So let's stop here then. I hope that you enjoyed the session. Please spend a minute to provide us feedback for the session. The feedback page will pop up as we are ending the session in a couple of minutes. Let me end with a reminder here. All webinars of the series are available for online consumption now once we did the recording here. So please, if you want to access this, please use the registration link to watch any of the other topics if you have missed them so far. You find the registration link here with the QR code, but also on the webpage. And with that, let me thank you for joining again, and bye-bye till next time.